Okay, good morning. Thanks a lot, Bjorn, and thanks a lot, Alexei and Matthias and Jairo for this kind invitation. So in this presentation, what I would like to show you is actually how spin dynamics in Dirac matter is affected, but can also be tuned by using proximity effect with other materials. Okay? So let's start with this picture, which actually shows how initially out-of-plane spin polarized wave packets propagate in polycrystalline graphene under the action of an in-plane Rashba spin-orbit coupling field, which is induced by the substrate, which is a typical situation that we find in the experiment. As you see on this snapshot of the time evolution, the wave packets extend from the initial injection point and diffuse and scatter in space because of the disorder grain boundary. And simultaneously, the spin polarization process and eventually relax in time due to disorder, due to many phenomena. Actually, you can really implement computationally very efficient methodologies in order to simulate the spin dynamics quantum mechanically in very complex disorder Dirac systems with millions and millions of atoms. And this is essential. For instance, if you want to know what happens to surface states of topological insulator, if you want to understand the spin dynamics and spin transport of this very specific situation, especially in three-dimensional systems, where the system becomes much more bigger scale, and where as soon as you have some disorder actually included, your effective two-dimensional model for surface states just fail to capture charge and spin properties. So actually, with those kind of methods, you can have a kind of quantitative comparison with experimental data, but you can also make a new prediction, as I will show in the rest of the talk. So I would like first to briefly give in some motivation about why two-dimensional materials are actually very promising for spintronic application. Then I will show you essential effects of the substrate on spin dynamic. We've been discussing what is the nature of spin relaxation in graphene. So you will see exactly what's going on, depending on if you have silicon oxide or boron nitride. And then I will show you that through proximity effect by interfacing graphene with a strong spin-orbit coupling material like TMDCs, like transition metal decalcogenide, you can generate giant spin transport anisotropy, spinel effect, and you can also sense weak anti-localization, so proximity effect through weak anti-localization. So I have to acknowledge the people that did the hard job in my group, and also my spintronic co-workers, because 4 or 5 years ago I was completely ignorant in all spintronics. So needless to say that we are very grateful to these two Europeans, Albert and Peter, for the discovery of the giant magnetoresistant that has so much impact our lives and our technologies, right? And especially spintronic came into our technology for let's say, developing data storage in a very efficient way. Now, the second revolution of spintronic is seen to be related to the fact of manipulate spin while they propagate, so that we can really develop and implement active devices. And this is the pioneering proposal concept by Datadas, SpinFET, has given rise to a lot of efforts. And actually now we know phenomena where we can generate, detect, and manipulate pure spin current by avoiding to use even magnetic materials. This is a so-called spinel effect. And also, with spin polarized or pure spin current, we can go and manipulate magnetization of other materials through the spin torque physics. And this really opens new doors in order to go for spin logics and information processing through manipulation of spin. The problem is here we need lateral spintronic. I mean, vertical spintronic is good for memory storage or even STT-MRAP, but if you want to do play these games, you need really to have, let's say, long room temperature spin diffusion lengths in a lateral architectures. And this is a problem actually that we're facing with conventional metals and semiconductors, because the figure of merits are not good enough to envision very complex architectures. So what makes graphene so attractive? Well, it has been presented by Ivan, by Alexei, by Christoph. Graphene can have gigantic mobilities. Okay, so this is now completely incredible, and even we can reach very high mobility in CVD graphene, which is an upscalable material. So that's key for technology. At the same time, the spin lifetime that we reach today, which are, let's say, 10 nanoseconds, are good enough really to go and to demonstrate that we can engineer spin, functional active spin device. So we can move on this search for spin logic technologies. But for me, one of the main interests of graphene is really that we can tailor, we can make graphene much more complicated, much more diverse through proximity effect. And this is really one of the essential, for me, the essential aspect which make these materials extremely promising for spintronic application. Actually, several years ago, this paper was mentioned by Ivan. We predict that when you put graphene on a magnetic insulator, and we also generalize this with YIG, which is a very high Curie temperature, you modified graphene property. Okay, you split the bonds, you open a small gap, so you already give to graphene properties that it didn't have because of too low spin orbit coupling. And if you coat a magnetic ferromagnet with graphene, it has been shown very recently that you can increase a lot the perpendicular magneto-anisotropy. And this is a key figure of merit for spin transfer torque MRAM. So if you increase this PMA, then you can reduce the energy, the switching current. And that's really reduce the energy consumption of this technology. So this is really work on the way. There have been predictions from the theory, and now experimental groups are trying to demonstrate in a fab environment. Finally, these spin logics, we already have this proof of concept. The spin FET, in last year, 2 Nature Com paper demonstrated you deposit MOS2 on top of graphene, and then you can manipulate, you can switch on and off this non-local signal. Okay, so it's kind of really a transistor that you can do by just interfacing to two-dimensional material. Also, there was a kind of experimental demonstration of a logic gates using multiple probe on top of graphene by the group of Kawakamishi and all the people in the US. So this is really today, it's happening today. And there are so many possibilities to play with the property of spin transporting graphene that there is really a big rush. So finally, I would like to mention that we have a consortium within this graphene flagship project where we try to gather most of the leading groups in Europe, not all of them, but most of them, and we try to move together in order to make those demonstrations and to transfer all the knowledge to companies. Okay, now as we come to this part where I would like to show you what's going on really when you have graphene on top of a substrate. Actually, a lot of expectation initially in 2009 when these papers were published, because Yao, in this paper, he predicted that the spin lifetime in graphene could be milliseconds. So it was just like 6 order or 9 order of magnitudes to what we knew. And also, the spin lifetime will be very high, close to the Dirac point. We're kind of diverging close to the Dirac point. 10 years of research from the first Nature paper by Barth and Weiss, and then huge amount of efforts, a lot of time spent. Mobility was raised, but spin lifetime remained much below microseconds or milliseconds. We reached 10 nanoseconds, which is cool, but we don't reach that scale. Additionally, the spin lifetime is not maximum at the Dirac point, but is minimum in monolayer graphene. Additionally, I mean, if we want to understand what's going on, you have to understand, it was raised in a previous talk, what kind of mechanism is driving the relaxation. So naturally, graphene is not a metal, graphene is not a semiconductor, but we knew 2 very well spin relaxation mechanisms for those materials, which is the Elliott effect, where spin rotates each time the wave packets scatter on impurity, or the Dyakonov-Perel, which is when you have a kind of homogeneous spin orbit coupling field, then the spin precesses, and then it scatters with impurity, and this changes the law between spin lifetime and momentum scattering time, and the scaling is reversed, actually. Turns out that it was shown yesterday by Christoph that we are very puzzling graphene, because when you put graphene on silicon oxide, when you make it cleaner, the spin lifetime decreases. So this is the Dyakonov-Perel scaling line. However, it seems that when you put graphene on boron nitride, you get something that looks a bit opposite, right? Just a bit, an opposite trend. So that's kind of very puzzling. What we know is when we have graphene on silicon oxide or when we have graphene on boron nitride, we have two sources of dephasing. We can have other contamination and things like that, but let's focus on these two that you cannot avoid, basically. One, which is the intrinsic spin-orbit coupling of graphene, which is very low. And then there is the effect due to the substrate or the two interface you cannot exclude, okay? So this will introduce an additional Rashba spin-orbit coupling thing because you break the mirror symmetry, and you will have some kind of impurities, and they can be well modeled by electron hole puddles. So let's forget about all the dirty that you can have. So the question we address first is, okay, let's try to model puddles in a very realistic way. Let's try to really take the amplitude of the Rashba spin-orbit coupling field that is introduced when you deposit graphene on substrate. What do we get, theoretically? So you can do that. You can have a tie-binding model. You can describe puddle very realistically because there have been a long discussion and modeling in the past. And then what you see, actually, if you look at the momentum scattering time for graphene on silicon oxide, on graphene on boron nitride, you will see something very important. That actually this momentum scattering time in graphene on silicon oxide is much smaller than the time precession frequency of the electrons because of the Rashba spin-orbit coupling field. Whereas in the case of boron nitride, you get something different. So you have a change of regime. In one case, you scatter a lot before the spin can process one full rotation. So it's really like a Dyakonov-Perel. And actually, so this is, I would like to show maybe this slide. This is just a movie. Let's see if it works. So this is a movie of the snapshot I saw, but this just show you that we can, at the same time we estimate the mean free path. At the same time, we look at all these wave packets, the spin components, precess, relax, so we can really extract the main spin transport length scale, right? So we have this oscillation and damping, so we have the spin precession frequency, and we have the spin relaxation time. So in the case where graphene is on silicon oxide, what do you get? If you look at this, the time the dependence of the spin polarization, so it decays, so you can extract the spin relaxation time, and you get a few hundreds of picoseconds, and you see that the spin lifetime increase when you increase the density of impurity. So it's purely Dyakonov-Perel. Actually, it's even the ratio between the anisotropy between out of plane and in plane spin lifetime is 1/2, which is exactly what we expect from the theory. So this is very conventional. On the contrary, when graphene is cleaner because it's on boron nitride, you get something different. You see that you have a lot of oscillation, so then you have more precession, which enter into play. And actually, if you compare the spin lifetime, you will see that you can get very large differences. But you have a common point, which is lower, close to the Dirac point, and the values, even if we have very small Rashba. We could put 0, we'll get to infinity, but it's meaningless. But few tens of microelectron volt is what we expect. We get this 10 nanosecond scale. The point is that we reach a regime where the momentum scattering time is so large that you can even enter a kind of ballistic situation and still spin relax faster than before a scattering on an impurity. So there should be an explanation about what this relaxation is coming from. And actually, the explanation was quite easy, is that graphene is not a metal. Graphene is very specific. Graphene has additional internal degree of freedom, which is Valley and sublattice pseudospin. And so when you have spin-orbit coupling, what you actually do is you just couple spin and pseudospin, and this entanglement is maximum at the Dirac point. Okay? So if you have more external degree of freedom coupled to your spin, it's clear that the decoherence is faster. There's nothing really sensational, but this is what's going on. We even show analytically somehow that what you actually need in addition to the spin pseudospin coupling is you need to have energy dependent spin precession frequency and some broadening. And as soon as you have that, even if you are in a quasi-ballistic or in a ballistic regime, you will get a relaxation of your spin polarization. So finally, we have this phase diagram, so the spin lifetime as a function of the scattering time. We see that if the momentum scattering is very short compared to spin position frequency, we have an increase, so Dyakonov-Perel, whether we have an opposite behavior when the system is very clean. So it's somehow in agreement with this, let's say, experimental data. Now let me come to the second part of the talk. As I told you, we expect a lot of innovation by interfacing two-dimensional materials, especially interfacing strong spin-orbit coupling materials with graphene. There are many proposals. This is a very nice proposal where you can try to inject spin-polarized electrons using TMDs, and you excite optically, and then you can measure maybe some kind of spin signal farther away. But this is a kind of very interesting proposal, and there are many more. So what we have been looking at using the models developed by Jaroslav and his team is graphene on TMDs, all of them. Okay, because they have really made a very fantastic work on an ab initio side, so they have the bands, and then they also elaborate the tight bending models that really capture all the features we need. So we need the band splitting, we need the gap, and we need the spin texture. I mean, if we don't have the correct spin texture, forget about your prediction. So they have to introduce by symmetry some additional, not only the intrinsic spin-orbit coupling and Roche bar, but they have a sublattice potential, and also they have a pseudo spin inversion asymmetry, which is very important actually for the spin texture. So we did basically the same kind of calculation, and using the puddle and using this model, and we found something extremely interesting actually. We found that if you have strong intervalley coupling, because of the spin valley locking inducing graphene, what you get is a very, let's say, a giant spin anisotropy between out-of-plane and in-plane spin transport. Whether if disorder is much smaller and scatters due to disorder is just confined to valley, then the asymmetry between out-of-plane and in-plane will be conventional. So this is our example here. The disorder scatter, and you see the dependence of the scattering time is typically of intervalley scattering, whether here it's opposite, and it's typically of intravalley scattering, dominant phenomena. And this is the value of the spin lifetime. So here we have for out of plane in red and in plane in blue. So you see that a certain density of defects of puddles, we get factor of 10, or we can even get a factor of 100. So this is completely unknown, I mean unprecedented. This type of anisotropy I've never seen in any type of interfaces. And here our simulation is using like this full quantum dynamics, but also we had an effective model that gives this symbol that's perfectly matched. So everything really matched, and we have this giant anisotropy in these interfaces. And we have some echo that many groups, experimental groups, are on the way, and some hints of confirmation of that have been reported. Okay, this is the case where you don't have intervalley scattering, so the anisotropy is very low, and something like a conventional Dyakonov-Perel. So now let me go to the spin-Hall effect, because spin-Hall effect is really a mechanism we would like to, let's say, engineer in these materials for the technology. So there have been a prediction 3 years ago by a group of Barbaros, where putting graphene on tungsten disulfide, if I remember well, he predict a gigantic spin-Hall effect at room temperature. Okay. Additionally, as Alberto Morpogo say, you can also look at low temperature, and you can have, let's say, an evidence that there is a strong spin-orbit coupling proximity effect, because we can see localization takes place. Okay, so this has been well discussed by Alberto. So these are our results. Mainly, they are very in parallel with what we did for the giant spin anisotropy. So here, this is a case where actually we have very strong intervalley scattering, okay? And here we look at the quantum conductivity as a function of the, let's say, the coherence length of the length scale. And what you see is that this conductivity, after some increase and saturation, then will go down, will decay. So this is well described by the scaling theory of localization, where you have the semi-classical value, and then you have a correction which is negative in this sense because of the accumulation of interference that drive the system to an insulator. And this is when we have switched off the spin-orbit coupling term. Okay? When we switch them on, actually, what do we get? We get an opposite contribution of the quantum correction. Okay? They'll switch on, and here we get an increase of the conductivity with the coherence factor. So this is really the weak anti-localization. You need to have this total mirror symmetry somehow with switch off or switch on spin-orbit coupling. So we have this. And we have this when we have intervalley scattering. But when we don't have intervalley scattering, again, we have something very different. And here, we see we have no localization effect. Okay. And the explanation is quite simple, actually. If you want to have a weak anti-localization, or weak anti-localization, you need to have the spin to rotate while there is a scattering, because then you need to rotate by pi, actually. And if you have intervalley scattering, because of the spin valley locking, you get this kind of process available, allowed. But if you confine to one valley, because of the spin texture, it's very difficult to make your spin rotate by pi. There will be precession, but the time will be very long. So there is a very strong difference between the type of disorder you have in the system that can impact the system completely differently. Now let's come to the spin-Hall effect. So this spin-Hall effect is very interesting, and there are actually two mechanisms that have been discussed in the past. One, which is initially the pioneer of this mechanism, was saying that impurities which locally introduce spin-orbit scattering with electrons would generate this separation of spin up and down population. And so this is an extrinsic mechanism because it is driven by scattering of impurities. The other one, actually predicted by Yarrow, is that if you have a bond structure and which have a special spin symmetries and texture, when you propagate in this bond structure with your electric field, then the spin naturally will deviate depending on their polarization, up and down. The same kind of mechanism, but really like intrinsically driven by the bond structure. And actually, we expect that this type of phenomena could yield to much higher spin-Hall effect, spin-Hall angle, which is the figure of merit. So what we did again is to try to compute brute force, fully quantum. No approximation is good just to verify that things match. But if you can get the full result, brute force with the quantum formula, it's much better. So we compute the spin-Hall conductivity, which is one of the two quantities we need. And we avoid to diagonalize anything. We really use kernel polynomials techniques. So then we can simulate system with median, very, very complex system. We can check this in very special case, which you just have in homogeneous Rajba or homogeneous intrinsic spin-orbit coupling. So then you make a check of the numerics. And this is what we get, which is more interesting. So the spin-Hall angle, it's a figure of merit of spin-Hall effect, will be actually connected. So it's how much you deviate your charge current into a spin current is related to this ratio between the spin-Hall conductivity and the dissipative conductivity. Okay? And here we see that already, even if you have a low disorder, there is a lot of difference between the type of TMDC that you use. Okay? So this changed a lot. But then what is a very interesting result is that, again, depending on the type of disorder and depending on the activation of intervalley scattering, you will get something very different. If you don't have intervalley scattering, then you get the spin-Hall angle in the order of the few percent, which is considered to be high. Whether if you connect the valleys, then things almost disappear. So it's actually interesting because it's opposite to the weak anti-localization. If you measure a strong weak anti-localization or prediction, we say your spin-Hall effect signal should be low and vice versa. Okay, I think my time is finished. Okay, so the rest is fine. I would just like to mention that we realize that if we want to understand spin-Hall effect in this system, we have to go a bit beyond just looking at the bulk or the, let's say, intrinsic property, like almost everybody is doing. Because in the measurements, you measure non-local signal. And we realize that when you do the calculation of these non-local geometries, you have a lot of background contribution to the non-local signal. So you really have to make also develop very efficient non-local transport techniques in order to get this non-local resistance and try to connect this to the intrinsic mechanism. And when you join both, then you get a comprehensive picture of what's going on. Thank you for your attention.